go over how to essentially do operations with complex numbers, something that you would have gone over in your Algebra 2 class. And I'll just begin by kind of giving you some background on what an imaginary number is. We've already had students while we're doing quadratics in our second unit. I've had two students think about the letter I, and that's where this kind of this lesson is going to help you kind of build on that. So they really came into existence when the study of electricity really kind of started to take hold, because mathematicians realized that we needed kind of something to take the place of, or the void of, the fact that not everything can be defined by real numbers. So that's where the idea of imaginary numbers kind of came up. And your understanding, really, you don't have to know that, but your main understanding kind of should start with the idea that this square root of the -1, right? We don't know what to do with that when you have the square root of a negative number. So we had to create an entire set of numbers called imaginary numbers to deal with that. So really, if you remember that I is the same as the square root of -1, and that I squared is the same as -1, that's pretty much, the extent that you need to know for this class of pre-calculus, okay? So a complex number will occur if we have a real number and an imaginary number added or subtracted together. So this idea is written as a plus bi. I know it says plus bi, but as you'll see later on, we will have subtraction, where a is the real part and b is the imaginary part. Again, that will always create what we call a complex number. And when you write complex numbers, make sure that your real part comes first. So this idea of like 5 plus 2i, make sure that your real number is starting it. Now, when we look at this idea of writing this square root of -a as a times the square root of -1, right, that essentially allows you to break it up using a property you learned in maybe the end of middle school or Algebra 1. And that's really what I'm kind of focus on when I express these two examples here. So I have the square root of -9. I know many of you already know the answer to this, but I'm going to show you the work. I'm going to do the square root of 9 times the square root of -1, right? And you know the square root of 9 is 3, and the square root of -1 is I. So the answer is 3i. Same idea for this one, the square root of -24. So I'm going to break down 24 into the square root of 4 times the square root of -1 times the square root of 6. The order is not that important. You'll see why I chose this order, right? 4 times 6 is 24. I know the square root of 4 is 2. The square root of -i we know is, the square root of -1 is I. And then I can't actually simplify the square root of 6 anymore, right? You could break that down into 3 times 2, but ultimately that's not going to help you take the square root of any number. So the square root of -24 reduces to 2i times the square root of 6. I'm not really going to make you do a whole lot with plotting numbers on a complex plane, but just to kind of show you how this works. Your real axis is your x-axis, right? So we can just kind of imagine going 5 tick marks to the left and to the right. Right, so each tick mark is 1. And then the imaginary axis will be the y-axis. Same idea, where I'll go up and down 5. And so this would be like a positive I and a negative I. So if it asked me to graph 3 minus 4i, that's a positive 3, so 1, 2, 3, and then a negative 4i, so 1, 2, 3, 4. So this point down here would be the point 3 minus 4i. You can do the same thing with -4 minus I. Go over to the real number -4, and then the imaginary number -i. So this is -4 minus I. All right, again, I'm not really that concerned about it, but showing you that you can actually graph complex numbers. Okay, let's get into kind of the meat of what we're doing today, which is operations. We'll start with adding and subtracting. This is as straightforward as it can get. When you add or subtract complex numbers, you're going to essentially think of your work with like terms in middle school. We're going to add or subtract the real numbers together, and then add or subtract the imaginary pieces together. So that's kind of the main focus for this. So let's do number 1 and 2. So number 1, I'm going to add 3 plus 2, which is 5. And then I'm going to add negative 4i plus 5i, which is just 1i. Do the same thing in number 2. Now with subtraction, your Algebra 2 teacher might have taught you to distribute the negative so that you can add. That's your choice, right? I mean, you guys are seniors now. You're almost in college. So I think you can subtract, but that's what I'm going to do. If you don't want to do that, please feel free to distribute the negative onto both terms after it and then add. So negative 5 minus negative 11 is really negative 5 plus 11, which is 6. And then 7i minus 2i is 5i. All right, this next one over here says subtract 2 plus 5i from 3 minus 4i. So 3 minus 4i is going to need to go first. And then I'm subtracting 2 plus 5i. So 3 minus 2 is 1. Negative 4i minus 5i is negative 9i. Okay, so that's kind of, that's the most straightforward of the operations, addition and subtraction. Let's move to multiplying. Going to get a little bit more challenging here. All right, so first we're going to just talk about distributing. When you distribute a constant onto a complex number, make sure you distribute to both terms. So this will be 8 plus 20i. And this fraction of 1/2 is going to distribute and give me 5/2 minus, and then half of 2 is 1, so minus I. All right, so not too bad with distribution. Let's talk a little bit about the cycles of I. You guys know that I is the square root of negative 1. All right. If I square that, squaring a square root, I'll show you the work here. So squaring that square root of negative 1, the square root is going to go away and just give me negative 1. You probably know that one from your work on this in Algebra 2. So I cubed would be I squared times I. All right, which is going to be negative 1 times the square root of negative 1, which I'm just going to say is the opposite of I. And then I to the 4th power is I squared times I squared, which is going to be negative 1 times negative 1, which is actually a positive 1. All right, and so these cycles, or I should say these 4 that you see, are going to continue in this cycle. So I to the 5th power is actually the same as I to the 1st power, so it's just the letter I. If you need the work there, I could show you. Right, so this would be I to the 4th power times I, which is 1 times I, or you get the letter I. All right, I can keep showing you if you want, but I just want you to know that as long as you know these 4, right, as long as you know I through I to the 4th power, you should be able to find any of them just using your understanding of exponents. So this is going to be the same. It'd be negative 1. This is the opposite of I. This is positive 1. I, negative 1, the opposite of I, and then finally positive 1. So let's try this one, I to the 37th power. So the way I do this is I do I to the 36th power times I, because I know that 36 can be divided by 4. So here's how I do it. I break that up into I to the 4th power and then raised to the power of 9. So if you remember back in your days of exponents, you do a power to a power, you multiply. So the I to the 4th power raised to the 9th power is I to the 36th power. So I to the 4th power I know is 1 from my work just above. So 1 to the 9th power is just going to be 1. Right, 1 times 1 times 1 times 1. So 9 ones multiplied together is just 1. So 1 times I would just be I. All right, so I to the 37th power is I. All right, that's not really the focus I want you to have here. I really want you to focus on these next problems with multiplication. And just like you've done in the past, you're just going to make sure you distribute everything. So 4 times 2 is 8. We have 4 times negative 5i is negative 20i. Then we have 3i times 2 is 6i. And then 3i times negative 5i is negative 15i squared. All right, so I'm going to combine some like terms. I have negative 20i plus 6i, which is negative 14i. And then this is kind of the main thing you would have had to learn from last year in Algebra 2, but I squared is the same as negative 1. So I'm going to replace that with negative 1. So I'm going to copy those down. Negative 15 times negative 1 is a positive 15. And so to finish this, I do 8 plus 15, which is 23. So 23 minus 14i is my answer. Let's do one more like this. So 3 times 2 is 6. 3 times 3i is 9i. Negative 4i times 2 is negative 8i. Negative 4i times 3i is negative 12i squared. All right, so same process. Do your like terms in the middle, which gives you just plus I. You know that I squared is the same as negative 1, so that's going to become a positive 12. And 12 plus 6 is 18. So 18 plus I. Now, this last one, you might notice that I'm about to do it. And we have the same thing, right? 4 and 2i are the same, but one says minus and one says plus. So let's see what happens here. This is kind of the crux of what we're going to do with division. So 4 times 4 is 16. 4 times 2i is 8i. Negative 2i times 4 is negative 8i, and this is negative 4i squared. Now, you should notice that my middle two terms, right, this 8i and negative 8i, are actually going to make 0. So now I'm just left with 16 minus 4 times negative 1, which is really 16, plus 4, or 20. And the reason this is interesting, right, that I put this question here, is because when you multiply complex numbers like this, where they have the same real and imaginary pieces, but just have the different operation, one is addition, one is subtraction, you will always end up making your imaginary pieces go to 0 and left with just a real number. So this is what these are called, is these are called complex conjugates, which we'll talk about in the next section. But complex conjugates multiplied together will give you a real number. All right. Now, this understanding kind of drives the whole idea of dividing. Okay. So with this last part of dividing complex numbers, you're going to see that when you really drill down and ask yourself, what do I need to do to divide complex numbers? You're not actually doing any type of division. All you're really doing is doing two sets of multiplication problems. Okay. The idea is you're going to be given a fraction, that has a letter I in the denominator. And this letter I, as you know, it comes from the square root of a negative 1. So we can't leave a square root in the denominator. Remember your understanding of that from Algebra 1 or Algebra 2. So what we have to do is we have to write this in the standard form, a plus bi. And the only way to do this is by multiplying the top and the bottom of your fraction by the complex conjugate of the denominator. Okay? So let's just do a quick note on the conjugates. All right, this is where you copy the real number, copy the imaginary number, just make the sign in between the opposite. So I copy down 2, copy down I times the square root of 5, but I just make the sign subtraction. This is really 0 minus 1/2 I, so the conjugate's going to be 0 plus 1/2 I. You don't need to write the 0. Same thing here. Write negative 3, write 4i, change the sign in between. All right, so that's how you write down the conjugate. So let's do a few examples. So this one here, we have negative 5 plus 3i divided by 2i. So I'm going to multiply by negative 2i over negative 2i. That is the conjugate of 2i. So I do essentially two of these. I like to do the denominator first, but it really doesn't matter. You got to do both. So 2i times negative 2i is negative 4i squared. Negative 4 times negative 1 is positive 4. Let's do the next piece, the numerators. So when I multiply this, I get positive 10i, and then minus 6i squared. So we know that that's going to be negative 6 times negative 1, which is really a positive 6. So 6 plus 10i. So now I'm going to write these back as a fraction. So 6 plus 10i over 4. Let's reduce that. Each of those numbers can be divided by 2. So I get 3 plus 5i over 2. It's probably how your teacher in Algebra 2 maybe would have taught you to leave it. but make sure you go one more step and you want to split it up into a real piece. So 3/2, and then your imaginary piece that has the coefficient 5/2 times the letter I. Okay, so this is what I'm looking for the solution. All right, let's do one more. We're going to divide 2 plus 5i, so 2 plus 5i divided by 4 minus I. So again, we just did a division problem. What you notice, we really didn't do any dividing. So what I'm going to do here is multiply by the conjugate of the denominator, which is 4 plus I. All right, again, I do the denominators first. It's up to you. I'm not going to show my work for the middle two pieces. I understand that if I multiply conjugates, like I'm doing right here, I am going to make those imaginary pieces become 0. So I'm not going to write them. So I'm just going to write 16 minus I squared. If you want to write plus 4i minus 4i, that's fine, right? Just make 0. So this is 16 minus a -1, which is really 16 plus 1, or 17. So that's my new denominator. Let's multiply the numerators here. Now this time I can't skip any multiplying, right? These are not conjugates, got to do it all. 2 times 4 is 8. That's going to be plus 2i plus 20i plus 5i squared. So I have 8 plus 22i, and then I have plus 5 times -1. That's really going to be minus 5, and 8 minus 5 is 3. All right, so let's go ahead and write this down as a fraction. All right, understanding that when we look at this, all right, I am going to go the extra step to make sure that I write it as a real number plus a imaginary piece. So we have 3 plus 22i over 17. All right, so I'm going to split it up by writing 3/17 plus 22/17 times I. You'll notice I wasn't able to reduce any of this. All right, and you can leave these obviously as improper. All right, so that's it for complex numbers. Don't forget to try the links for this for your practice.